Okay, so welcome to ME 589, Sustainable Design, Technology and Environmental Systems. I'm Steve Skurlos. I'm a faculty member in mechanical engineering as well as civil and environmental engineering. This course has a long history. It's evolved quite a lot. And as we're going to talk about today, it's evolved even since maybe some of your friends took the course a year ago. So I'm particularly excited to present the first day of class here. And it's kind of a packed session. So we got about 80 minutes here. I'm counting, maybe 78 minutes. And I think we'll be able to get through some framing of the sustainability question that brings us here to this class, develop some definitions, working definitions for the class. We'll have an in-class exercise related to the reading that some of you may have been able to do before class started, and then get into the details. I know a lot of you are here to learn about regarding the syllabus schedule. And we're wasting no time, so assignment 1's being released today, or some of you may have seen it already. Okay. So the first question I think we need to answer before we move anywhere is why this issue doesn't go away. There's really, I think most folks know, environmental issues have been at the forefront of the public conscience at least since the 60s. Right, so you're talking 40 years or 30 years, depends how you count. And you can either take two positions, right? One is that really we've solved this issue, and there's just a group of people out there, maybe some of you, who need something to talk about. That's one way to look at it. Or the other is that we've been working on this, and we're either just barely keeping our head above water or we're sinking a bit. Depends on your perspective. And to get at why this environmental issue doesn't just go away, I'd like to ask for a volunteer to answer a question. The answer to that question will be very much similar to the answer to this question. So can I take a volunteer to answer a very important question? Right up here in the front and center. Being bold, being early, getting a good seat, you get rewarded. So 25 cents coming your way. Yeah, big stage here. Big stage here. All right, so my only question for you is, would you prefer your payment as a quarter or 25 cents?
I prefer a quarter.
Okay, you sound very sure about that. I did say it relates to this question. You're sure?
Sure.
Okay. Now, how many people would have gone the same way with that? Pennies, anyone? Nobody? Really? Really, I don't want them. All right, that's fine. That's fine. So anybody, why the quarter instead of 25 pennies? Our friend here, you have to earn your keep, right?
Convenience.
Convenience. Can you be more specific? Maybe it's convenient to me to have exactly 12 cents to give to the change person at the store.
It's easier to transport and easier to spend. Easier to store.
Transportation, easier to store. I think there was a hand in the back. Go ahead.
They work in laundry machines.
Laundry machines. So you do your laundry. Thank you. There's one of you. What else?
Occupies less space and weight.
Less space and weight. So if you got a small hole in your pocket, as I often do, maybe less likely to fall through it. Right? Anyone else? For me, growing up, it was video games. That was a big one. Pac-Man. You put a quarter in it to play Pac-Man. I guess these days you got these things at home, right? So it's kind of a funny thing, though. If you were to ask my wife what she would prefer, she would have said the pennies. Right? Drives me kind of nuts, but she's that person in line at the drive-thru picking out those 12 cents. I feel like we're in a hurry. I'd rather just deliver the quarter and let the other person deal with it. Now, the point is, with the quarter and 25 pennies, right, if you ask an economist, it's the same. 25 cents, 25 cents. But clearly, with the resounding majority, the unanimous decision that you'd rather have the quarter, there is more value in that quarter, at least to this group. Right? Different people have different values, right? So my wife would go with the 12 cents, or the 12 pennies there. So the market decides what the price is for something, right? And maybe you would give me 30 cents for a quarter if you absolutely needed a quarter to put into the parking meter or the laundry machine, right? So the first point here is that the markets They're not something magical, something that exists. They're really just reflections of us. People have different values. And if we think that there's an environmental issue that may not be taken care of to the extent that we would like, then we have to ask the question, okay, where is that value really coming from? Who's setting the price? Really, we are. And the second point here is that the value we place on the environment comes through science, right? What we learn, right? It may be undergraduate, it may be graduate courses. How many people are taking their first either environmental science or sustainability course? Right here. Okay, so that's a higher fraction than I would have expected, 35, 40% if I had to guess. So you may have learned about sustainability, environmental issues through the news. It's kind of a dangerous place if you know about that, or maybe looking up media clips or what have you. I mean, these are things that are not easy issues. Okay. These days we're teaching undergraduates in engineering about some of the core science issues related to environmental sustainability. Some of you haven't seen that. So we have assignment 1, which was released, that will take you through a review of some basic environmental science topics that we'll be using over and over again in class. Third, the distribution of cost versus benefits matters. So let's just say there's 100 people in the room for simplicity. And let's suppose that we're going out to lunch. There's 2 things on the menu. There's hamburger and there's pheasant. And if you're a vegetarian, I guess we didn't create an option for you here. So everybody's going to pay their own way. The hamburger is going to be $5 and the pheasant's going to be $105. Okay, paying our own way. Everybody's buying lunch. Who's picking hamburger? That looks like everybody. Pheasant? Nobody. I think there's one thinking about it back there. So nobody. Okay, well, has anybody had pheasant before? Yeah, is it good? I've never had it. All right, so some people might be willing to pay for it. Well, let's just do this a little bit differently. Instead of everybody paying their own way, how about we add up the bill and divide by the number of people here? And that's how we'll divvy out the cost here. So is anybody going to get pheasant now? See a couple people smiling. It's like the guilt. Like, yeah, I think I might do this in reality. I've never had pheasant before. I've heard some people say it's good. If I have it, great. It's $105. That's $100 more than my hamburger. There's 100 people. That's just $1 each. I'm worth it. You can pay it. We're good. Right? Anybody else doing it? Really? You see meat and pheasant? Really? Come on, somebody will do that, right? I mean, it tends to be that there tends to be more than one person like me out there who's going to just sort of, okay, well, if pheasant's available, I'm doing it. It's a low cost to everybody. We're sharing it. It's fine. I don't even notice it. Right? This is an instantiation of what's called the tragedy of the commons. How many people have heard of the tragedy of the commons? Okay, that's a majority. That's 60, 70% if I had to guess. So it's the same idea, right? It's when I benefit as an individual, but the costs of that benefit are shared, I might behave differently than I might have otherwise. So it means things that we share tends to lead to what we might call suboptimal decisions, at least from a societal point of view. From my standpoint, I wanted pheasant, great, so that was optimal for me, but maybe not for society. Right? This is what the tragedy of the commons is. So resources that we share tend to be abused. When we make collective decisions, they sometimes, or more often than not, tend to be greedy. So we got to look out for things that we share. So you want to know why the environment is an economic special case. It's as simple as the fact that we share it. Right? Either at the local level, we might share the Huron River. From a climate standpoint, we certainly share the CO2 concentrations in the atmosphere. Right? So there are a lot of reasons why this issue just keeps coming up and coming up. It's challenging. Not only are the issues complex, but from a technical standpoint, but there are also complicated social factors and economic factors at play here. So we can ask the market to solve the problem. And to talk about this one, I brought along a slide rule. How many people know what a slide rule is? Okay, that's just over half. How many people know how to use a slide rule? and could teach me, because I don't know. Go ahead, a little bit, kind of something about logs, right? I don't know either. This was my dad's. $50 in 1963. That was a lot of money then, and it was particularly a lot of money to him. He didn't have a lot of money at that stage of his life. So he happened to give it to me. I don't know how to use it. $50? Anyone? Going to give me $50 for this? Really? Come on. Look how environmentally friendly it is. It doesn't use batteries. You burn calories using it. Nobody really? How about $1? Somebody give me $1 for it? Okay. All right. So it's my dad, so I'm not giving it for $1. $50 I would, but not $1. But look at the slide rule. It's in great shape, right? Has it changed? Doesn't look like it. It still operates. The better, more likely answer is that we've changed, right? There are other ways to compute sums and multiplications than the slide rule. And so we moved on, and this is pretty much worthless, right, except as some collector item. So the point is, with the market and the slide rule, that really it's a reflection of us, right? I come back to that point again. Because if you think that maybe there's some issues with the air or the climate or the water, and you're asking the market to solve this problem, the question you should be asking is, what am I doing about it, and what's everybody else doing about it, right? Because that's what the market is. It's just a reflection of us, right? The slide rule remained the same. We changed. And everybody's been through Econ 101. You remember these supply curves and these demand curves and the market clears where they cross and all that business? You're going to get some of that in a few weeks because we'll use those tools in this class. But it's a very simple model. Right? But when you actually look at the assumptions of the model, they're not only simplistic, they're wrong. Right? All participants have perfect information about the future. Right? I wouldn't be here. I'd be playing the stock market. I'd be playing Vegas is what I'd be doing. Perfect competition. Go to your search browsers and ask that question. Prices being absolutely accurate and up to date, reflecting social costs, one individual transaction moving the market. I mean, all these things are not true, and it's really easy to come up with counterexamples, right? There's nothing that cannot be bought or sold. I like that one. I think of my dog. You can't buy him for $50 even. All deals being instantaneous. So if you want soda, you snap your fingers. It's right there. Magically, the money disappeared from your wallet. Transaction just took place. You didn't have to do anything. And then, by the way, you could have gotten like 4.5 ounces of soda if that's exactly what you wanted, right? Because all investments are infinitely divisible. The point is, the market is as complicated as we are. These rules actually do a decent job describing market behavior, but they certainly don't describe us. So, you don't want to confuse the map, things we use to understand the market, with the territory, which in this case is us. It leads to a nice quote. Comes from Natural Capitalism. We can use markets as a tool. If you want people to use less gasoline, raise the price of gasoline. You want people to value carbon, put a price on carbon. Right? So you can use markets as a tool to serve us or to serve sustainability ends. But the market isn't some creature that's out there living on its own, that somehow takes care of environmental problems, as some would suggest. Right? It's a bad master and an even worse religion. It's something that we use. And one of the topics we're going to discuss throughout in the various sections of the course is how economic instruments, often through policy, can be used to serve environmental ends. So policy is part of this. Now we can look at government. We can look at the key laws on the books, ones you've probably heard of, at least if you've been spent some time in the U.S. Right? Clean Air Act, Clean Water Act, Safe Drinking Water Act, RCRA, Superfund, Safe Drinking Water Act, Toxic Substances Control Act. You see these, sort of a laundry list. You're going to read about these with assignment 1. What strikes you immediately when you look at these laws on the books? The dates are old. What else? Not a lot there happening with respect to pollution prevention. Right? I don't know who said that, but would you agree that these are probably looking more at the end of pipe and to the atmosphere or the watershed more than trying to prevent pollution? That's definitely true. What else?
Is that only one agency, the EPA, that you're representing there?
The EPA,
I would say that what I noticed is that, I mean, there are other agencies out there that also contribute to environmental law.
right, so give an example.
Might be missing there.
So give an example. Particularly related to pollution prevention.
Yeah, OPA 90, I think is up there, with the oil pollution
Right.
prevention act. That's one that goes in 90.
So there are regulations that often fall under, so if you think about the laws, right? The laws determined by Congress, and Congress usually specifies who shall enforce, right? So the executive branch does the enforcement, and there's some selection there. With respect to the EPA, I think what you're referring to are these costs, right? So with respect to EPA regulations, the regulations that EPA enforces, associated with these and others, right, these are the big ones, something like 2% of GDP, so that's like $200 billion. Right, there's a lot of money involved with just maintaining or staying where we are with respect to environmental protection. And EPA claims that for every dollar we spend, there's like $10 to $100 of gain. So that's $2 trillion to $20 trillion of benefit. Right? And those are in like 1997 dollars. So why are we still talking about this issue? Pollution prevention. Why do we care about pollution prevention? What pollution needs to be prevented that is not adequately represented by these regulations, or these laws, I should say? Go ahead.
Greenhouse gases?
So climate change is a big one. All right, so we put that one first. We don't have anything at a national level yet that's seriously tackling climate change. Now, you could look within a specific industry. There are regulations in automotive that help to address climate change and recently amended CAFE standards, proposals for 2020 and beyond. How about these other areas? I mean, do we still have air pollution problems? Do we still have water pollution problems? Yeah, so a lot of you are familiar with that. Now, this course is not a course where we're going to be talking about these issues. There are other courses on campus. In fact, this class, when you go back 10 years or so, used to cover all these areas in great detail. And now there are other places you can go on campus, including undergraduate courses. In fact, there's a recently revised course, actually just revised this semester, a course in sustainable engineering at the undergrad level here at U of M. And I'm a part of teaching that class, and it felt kind of funny to spend 3 lectures in ME 589 talking about climate change, and give it the same day to an undergraduate group at a 200 level course. Okay. So what we're doing now, the strategy we're taking in the class, we're going to spend about 20 minutes at a very high level talking about what some of the issues are. Refer you to some resources. You've got assignment 1. The rest of the term, we're going to be talking about what we can do to assess, prevent, and design around and for these challenges. Okay? So don't get the idea in the next 20 minutes or so that we're going all gloom and doom on you. But we have to show these issues respect because they're big ones, right? We talk about climate change. I think this is a difficult one, especially for those of you who have not taken a class where it's been dealt with in some scientific sort of treatment. But if you look at, and the basic story here with climate change, there's certain things we know and there's certain things we don't know. There's certain things that are unknowable about climate change until it happens. But what we can be absolutely sure of is that CO2 concentrations have varied in the past, but they have not varied to the extent that they're varying now. So we're talking about CO2 concentrations here. So it used to be you'd say that the only sure things in life are death and taxes. But you can add to that about a 2 ppm or 2 part per million rise in CO2 concentrations. Because that's been going on now for a good long time, decades. And that's easy to measure. Right? There's no argument about whether CO2 concentrations are rising. There's no argument about whether carbon dioxide and other gases in its class contribute to warming of the planet. I mean, just look at the moon and look at Earth, and the Earth's a little bit warmer. It has something to do with the atmosphere. And you know this. For those of you who've braved the Michigan winter before, you know that a cloudy night is warmer than a clear night. And it's the same thing. It's just gases, in that case water vapor, just protecting basically keeping the infrared energy at the surface of the Earth. That's all it is. CO2 does the same thing as water vapor. Thankfully, we don't have as much of it in the atmosphere, so that'd be a real problem. But we've got CO2 concentrations, other greenhouse gas concentrations rising in the atmosphere, so the Earth will get warmer. And there is pretty much where the certainty ends, because the next question you ask is, okay, well, how much, how fast, and what are the impacts going to be? And there's no way to know. The only way to know is to go out there and construct another Earth, find another solar system, drop that artificial Earth with its artificial people and it's artificially just out there and observe. And we kind of let things go business as usual, or maybe not. Maybe we need two Earths, right? So we're going to do one over here, and it's going to be business as usual. And here we're going to take some action. We're going to compare the two, right? You just can't do that, obviously. So there's going to be uncertainty about how fast and what the impacts are going to be. But there are some logical impacts. And some of the impacts are going to be good, and some of them are going to be bad. But even the good ones are going to take some adapting to. And adaptation usually means money. Right? So if the water moves or if it comes down in different amounts than it used to in the past, folks are going to have to move, and folks are going to have to build infrastructure systems to manage that water and its new flow rates, for instance. Bugs are going to respond. Diseases are going to move. These things are going to happen. What's the impact on agriculture? Is the belt's going to move north? I can't tell you. I don't know. There are people who will tell you they know because they've studied these things for their whole lives. But what we can say is that we are increasing uncertainty about the future. How many people have taken a course in Lean or Six Sigma or quality control? We got some people who've taken those courses. Okay, so maybe a third. So what does Deming and Schuhart and Taguchi, what do they say about variation in production? Yeah, variation's bad, right? Being on target with minimal variation with your product, that's a good thing, right? Well, if we think the climate's about right, we have set up our cities around it. Our ecosystems are rather used to it. Well, in that case, we may not want to increase uncertainty about the future, but we can be sure about that, and uncertainty is increasing about the climate. And this will come up a fair amount as we move forward. But climate's not the only issue. I will be a little bit surprised, although I don't know the answer, that climate change has led to 50,000 premature deaths in the U.S. per year. I'll be a little surprised. I don't know if that's the case, kind of hard to know. But when we talk about air pollution, this comes from NOAA. Roughly 50,000, they estimate, people die prematurely in the U.S. due to bad air. In Europe, there was a study, I think this comes from 2005 or so, about 300,000 people in the EU die prematurely per year. They say the average person in the EU lives 9 months shorter life on average because of air pollution. Okay? Obviously, there's a lot of uncertainty here, but there is a consensus that bad air kills people. You see on ozone action days increased visits to the hospital. Right? Hospitals get busier. Cardiac issues increase. I mean, that's fairly well known. Okay? Down here in the lower right, you can't see this. This is a study by the National Academy of Sciences urging the government to take these premature deaths into account when doing cost-benefit analyses with respect to clean air and pollution prevention. It's not just a U.S. issue, right? It's also a global issue. The World Health Organization estimated that about 1.3 million deaths occur worldwide, premature deaths occur worldwide due to outdoor air pollution. Okay, and you may have seen, not to pick on Beijing here, right? These were just convenient pictures, right? Anybody from Beijing here? Okay, we got one soul out there. Hey, you think this is an adequate representation before the rain and after the rain, or is it a Photoshop?
Looks pretty accurate.
Yeah, some folks have been there. I've been to Shanghai and would argue that. And, you know, it's not just in China, obviously, right? My folks live outside of Los Angeles, and some days it sure looks like this to me. So, you know, this is a global problem. If you want to learn more about smog, photochemical ozone creation, or even stratospheric ozone, there's some archive videos available. You're going to read about it, but also some former class sessions from 589. Okay, so some pretty heavy stuff on the air pollution side. How about water? Well, you know, there's a simple way to look at water. You can just ask, how much water is there? And where are the people? I'm talking about fresh water here, the usable kind. You know, here we look at North America. We've got about 8% of the world's people, 15%, almost twice that percentage in terms of the world's fresh water. So we're good, no problem. South America looking good. Asia maybe not so much. Africa maybe so-so. Well, this is missing part of the picture, right? If we look at regions within, we can talk about physical scarcity of water. You know, the Southwest isn't going to surprise anybody, although the Southeast has been doing its share to catch up. There have been some very significant droughts in the Southeast recently. Orange is approaching physical scarcity, where there just isn't enough water to feed the population. So basically, you got to import to deal with it. There's also an issue of economic scarcity of water. So this is not just the sort of the physical availability of water, but the economic access to that water. You see that as a big issue here, estimated in Central Africa and parts of India here, Southeast Asia, Central America. Okay, so water availability is an issue. Then there's the question of what we do with the water once we withdraw it from the ground. This is a metric of biochemical oxygen demand. How many people know what biochemical oxygen demand is? Okay, our water people, there's like 5 of you. All right, you're going to have to help your classmates in a few lectures from now. You know, I think that tends to be in mechanical engineering a little bit of a bias towards air relative to water. Water is important. BOD is a metric of oxygen depletion potential of a waste. What you're looking at here is for the industrialized countries, the OECD countries, and the non- or lesser industrialized countries, the non-OECD countries, emissions of BOD in megatons per year. And you can see from different sectors, from households, from agriculture, obviously the big ones. And you see it growing with time. From blue is 1995, 2010 is red, and green is estimated in 2020. So we withdraw the water. As populations rise, we're going to withdraw more water. And then we load it up, not just with BOD, oxygen-demanding waste, but other pollutants. And you know, then what? Then you know, somebody else eventually uses that water, or we got to pay more to clean it up. So there's a lot of concern moving into the future about stress and increased scarcity with water. So what you're looking at here on the left-hand side is a plot of percentage of water withdrawal relative to the total available. So in orange here is an area that is estimated by 2025 here at the top to be withdrawing more than 40% of the available water in that region. Okay, so again, imports become very important. You can see water moving around, or people moving around, because people need water. As populations grow, you know, there are projections going out to 2050, anywhere from 2 billion to 7 billion people either experiencing water stress, and stress is defined here as where the demand is greater than the safe supply, or just outright shortage. All right, so there are concerns about it, not just because of population growth, but because of climate change. Now, climate change isn't going to reduce the amount of water on the planet, right? Obviously not. The water is conserved. but it does move it around. It does put it in forms that make it less easy to use. It also changes the distribution, right? You know, some of those rainstorms last week could get you imagining some of the things that people are concerned about with respect to downpours, right? Droughts in some places, downpours in others, and you know, some concerns about stress across the board. Now, who knows if this is going to become a reality or not? But you know, we shouldn't forget water as we're thinking about air. When we get to the resources, whether it's our material resources, our energy resources, wastes, we think about the global majority. I think it's pretty clear that these laws are not doing a whole lot in those areas. The Resource Conservation and Recovery Act does a lot to track wastes from cradle to grave, but not a whole lot to prevent the generation of waste. And one thing you could ask is, to what extent do those laws address resource scarcity, efficiency, protection of biodiversity, the accumulation of electronic waste? We all love our gadgets, but they tend to be loaded up with toxics. We could talk about the prevention of using those toxics, right? The laws on the books nationally in the U.S., not doing a whole lot. There are certain states, the Northeast states and California, in a few examples. There are other examples, too, that are addressing some of these issues. But at a national level, still not a whole lot. Our friends in Europe, even in parts of Asia, are actually doing a fair amount in this area. I just picked Europe as an example. If we look at their directive on the eco-design of energy-using products, there they take outdated design strategies for product, particularly energy-using products, and essentially ban them. Right? So either strongly advocating, labeling, or banning design practices. Right? So connecting actually the reach of legislation and policy right into the designer's toolbox or computer. The accumulation of electronic wastes in Europe, the Waste Electric and Electronic Equipment Directive, WEEE. Any product that draws an electric current, so it could be an appliance, it could be a computer, a consumer electronics device. If it draws electric current, consumer product, the manufacturer is responsible for taking that product back and recycling a fraction of its mass back into the technosphere. Right? So it could be up to 80%, 60 to 80%, depending on the industry. Okay? So that's the WEEE directive. Prevention of toxics in the environment. Right? So basically banning the use of certain materials unless there is no substitute in an application that's important for people, essentially, for society, like certain medical equipment. But you can think about lead and solder. You can think about cadmium in wires shielding. Some toxic metals, just plain banned. PCBs, banned. Okay. So there's a lot going on in parts of the world, certain parts of the U.S., but our national law is still not there. And that's exacerbated, of course, as we've mentioned already, by the fact that the population is increasing. So this is our population clock, from last Thursday. Estimated by the U.S. Census Bureau, about 312 million people in the U.S., just shy of 7 billion on the planet. Okay, and about a year ago, I went to the clock and got these numbers. So if you look at the U.S., we've increased by about 2 million people. And the world has increased by about 100 million people. Now, there are about 300 million people in the U.S. Okay, so 1/3 of the U.S., roughly. Okay. Now, some of you, how many people have done an exercise where you sort of track your own footprint and you ask the question, how many planets would it take, planets full of resources would it take if everybody on Earth lived at the same standard of living you do? Has anybody done this? Okay, so a bunch of you have. So what number do you get? Like, what's the order of magnitude? Is it like 0.1 or is it 50? What is it? 4? 4 to 6? Anybody going to argue outside of that range? Okay, let me use 3, just because 3 is a convenient number. I think a lot of the calculations do say 4 to 6. But what's interesting here is the world has gone from 6.8 to 6.9 roughly billion people. That's about 100 million people. So that's 1/3 of the U.S. So if it takes 3 planets for everybody in the world to live at U.S. standards, then that increase in the last year needs a planet. And it looks like that's an underestimate if it's 4 to 6 planets, right? Now, clearly, there are inequities in consumption and income, not just around the world, but in the U.S. But that is a bit pausing and a bit sobering to think, right? Clearly, most of these people do not live at our standard of living. In fact, if you go to the Human Development Report from '98, they estimate that 20% of the world's people consume about 86% of the resources. And the bottom 20% only about 1% of the resources. Right? And I think we all know that information is global. And you got to wonder, what these 20% are thinking in terms of their own development, right? And their views of developing the same way that we did. Right? So what's going to happen there? Right? And population's increasing rather quickly. Clearly, I see this 100 million just in a year. I was born in '72. That was 4.1 billion people. So we're at about 7 billion people now. So roughly 3 billion more in about 40 years. It took 10,000 generations to get to 2 billion. It is slowing down, but not very quickly. It's expected by 2025 we'll be above 9 billion. Okay, probably by the end of the year we'll be at 7 billion. Right. So it's a lot of folks, and we need to ask this question. Where's it going? As the rest of the world catches up, as we advance ourselves, we need to ask the question: how are we going to do it? And the idea of sustainable development. How many people have seen this definition before? Meeting the needs of the present without compromising the ability of future generations to meet their needs. Okay, about 40%, and strangely, they're all sitting in the back. I have to think about that as to why. Why is that? Because they know already, maybe. But it's a simple idea, right? Sustainability is about the future. And a lot of times, people forget that. I use this picture. Think of this little girl, and she's in her swing, right? So she's pretty hopeless. If she wants to get out of there, she's going to need a little help, right? She's looking to the future. She's wondering, okay, what's the world going to be for me, right? What am I going to inherit economically, environmentally? What's society going to be like? Thankfully, she's not really thinking about that. But us looking at that picture might wonder, what that's going to be like in 20 years or 30 years, right? On the path we're at, it just ain't going to fly. Climate change, clearly an issue. Air pollution, water pollution, the consumption of resources. We don't have 4 to 6 planets. Human population growth, and the disparity between the rich and poor, which generally creates conflict. Right? So we're going to tackle all this, and the good news is we can. I mean, we shouldn't think for a minute that we can't. It's really about the will to do it. That's the question. It's going to take a systems view. It's not just technology. It's economics, and it's thinking about those broader social factors. We as engineers, how many people in the room are not an engineer? Thank you for being brave, all right? Now, this is great. Actually, non-engineers do well in the class, and they add a lot. So we welcome you here. Oftentimes, there's more. We as engineers, which is the majority in the classroom, we tend to think that technology is the solution. We're solving problems, right? But you don't get this without technology. I think this is a nice picture, so I use it. The idea that technology is a spigot here. And we look at the natural resources, the energy resources, material resources on the planet. We think about the ability of Earth to absorb the pollution, right? That depends on technology. Now, there are technologies that can throttle back the spigot, the valve, just as well as accelerate it, right? But on balance right now, it's looking more like the left-hand side. We need to learn how to harness technology in a way that we're using the resources we have Not just material and energy again, but the ability to absorb the pollution at the rate that Earth can handle. Or we can get out too, right? We can find other planets, and that might work too, but it doesn't seem too practical right now. So, that's a story on technology. So we talk about technology, and it's one way to think about it, right? As a solution or as the problem. There's a master equation here. How many people have seen what's called the master equation or the IPAT equation? Okay, so it's about the same. We saw the Brundtland definition, about 20%. So this is a simple equation. There aren't too many equations in this class, and this is the easiest one. Environmental impact equals environmental impact. On the right-hand side, population times gross domestic product per person times the environmental impact per unit GDP. You multiply across, you get environmental impact equals environmental impact. We've talked about population, it's increasing. We've got a presidential election next year. Imagine one of the candidates running on a platform of lower standard of living for all, right? Taking a chicken out of every pot, right? Oh, that's a dated joke. All right, I thought somebody would laugh at that, but that goes back like 70 years. Okay. Anyway, so these two terms, you multiply them together, it's increasing, right? So our hope really is in the last term to reduce the environmental impact per unit goods and services we produce. And if we believe that climate change is an issue, that energy resources, material resources, water, air, these are things to think about, then, and we could put any of them on the left-hand side here, right? Then we got to look at the last term here, right? That's a technology term. It's the ability to reduce the environmental impact per unit goods and services we produce, right? Technology can do that for us. But it's not just a technology issue. It's also an economic issue, right? I mean, we've got electric cars and we've got windmills. Why aren't we using them more than we are? There's economic issues there, right? In this class, we'll talk a lot about the environment. We'll talk a lot about economics. We'll talk less about the third important factor, which is the social side of it. We will talk about it some, but we'll be directing you to other classes where you can learn about that if you're interested. Okay, it will come up in our term projects and our debates and some of the case studies we have. But we can't dedicate a whole class to it because these are, it's about people, right? You can spend your life studying people. But there's really three factors here. So, coming now to the topic of the class, sustainable design. There's two major elements to sustainable design. One is the design and deployment of new technology, and that's not what this class is about. Now, some of you are water technologists, some of you are energy systems technologists, some of you are transportation system technologists, right? Mineral extraction technologists. We obviously can't, teach design in those specialties in this class. That's not what we're here to do. We'll look at a lot of examples, don't get me wrong, but we're coming from all different backgrounds here, right? So what we hope is that you're going to become amazing designers in your field. Get ingrained, get in passion, live it, and use sustainability and the assessment of system designs to inspire that technology development, to evaluate it. And that is what we're covering, particularly the economic and environmental assessment pieces of that. Okay, so that's what we're doing here. Before I go on, is it clear, at least in broad terms, what the challenges are and what we're trying to do in 589? Because we'll start now narrowing in on the syllabus. This is the big picture stuff for the day. Is this making sense? How many people have taken a course in life cycle assessment? All right, this is more like 10% now. So we went from that 20% down to 10%. And I actually would have guessed it's more. I like to use pictures. So life cycle assessment in a picture might look like this. We'll spend class periods talking about life cycle assessment, but I just want to give you the idea here. It's a tool for the environmental assessment of technology. Basically, you take a product, could be a manufacturing process, could be a service, and you look cradle to cradle, all the unit operations embedded in it. So if it's a coffee maker or maybe a car, what are the materials that go into it? What are the manufacturing processes? How is it used? How is it distributed? What happens to it at the end of life? Are there components that are remanufactured, etc.? So those are the unit processes that fall within the system boundary in a life cycle assessment. What a life cycle assessment is, and it sounds like all like sexy magic, but it's just accounting. That's all it is. It's kind of boring because all you do in a life cycle assessment is you look at the unit operations and you look at the materials going in, the energy going in, the emissions going out, the air emissions, the water emissions, the products. Sometimes there's allocation issues and co-products, as some of you are aware of, and we'll talk about this term. But it is brute force, and it is for the patient. Okay? And there's some amazing courses on life cycle assessment on campus. You hear more about where to go for those resources. We're not going to talk about how to do a life cycle assessment. We're going to talk about here the characteristics of good life cycle assessments and how to apply them in design. Okay, that's what we'll be doing in this class. So let's look at an example of an aluminum-intensive vehicle. You'll see some more of this later in the term, maybe even Thursday. That's a paper that some of us did here at U of M, thinking about lightweighting a car with an aluminum-intensive body in white. Okay? So the question here was, how quickly do you get the production emissions back? Because I think many of you know that aluminum, when you produce aluminum, it takes more greenhouse gas emissions per kilogram of aluminum than the functionally equivalent amount of steel. Okay, so this equivalent body in white in steel would require fewer greenhouse gas emissions in production. Okay, but it will weigh more. So there's a trade-off there, right? You have higher production emissions with the aluminum-intensive vehicle, but the more you drive it, the more you save because it's lighter and the fuel economy is higher. Right? So if you don't drive it at all, right, the aluminum-intensive vehicle, not such a good idea. Just going to park it in your driveway, never going to use it. But you buy cars to use them. After some period, you get some payback. And life cycle assessment's an amazing tool for something like this, right? So we can look at the paybacks. So, 3.5 years, if you look at the black line here, drive it around, maybe 12,000 miles a year. I think that's what we assumed here. It's interesting, though, life cycle assessment tells us, this is the average kilogram of aluminum from the U.S. The average kilogram of aluminum from China has a higher footprint with respect to greenhouse gas emissions. So it's going to take longer to pay back. And it's not like the U.S. is, that great. I mean, if you get your aluminum from Brazil, that payback period is going to be a lot shorter than 3.5 years. Right? It depends on the electricity sources and the technology used to make the aluminum. That's the key factor. Okay? So in different parts of the world, there are different emission factors on average. And clearly within a country, there are variations also. Right? So life cycle assessment is great for answering questions like this. What are the greenhouse gas paybacks? But there are some questions that life cycle assessment does not answer. And these are some of them. Right? Would people buy those vehicles? Would producers have an incentive to make them? And if they did, where would that aluminum come from? Right, where's aluminum being made today? And if that production capacity of aluminum needs to expand, then where's that expansion going to happen? And if that supply chain needs to react, is the price of aluminum going to jump? And if the price of aluminum is going to jump, then are people going to buy them? Right, so it's sort of a complicated system when we think about some of the economic interactions that occur inside of this, what appears to be simple question. Right? I mean, ultimately, if we're thinking about greenhouse gas reductions from vehicles, what we really want to know, maybe it's not what's the best technology, although that's an important question, but what are the best policies? And how are we going to study that? I think making a case of economics being important and social factors being important, we need to look beyond the use of LCA. LCA is a foundational cornerstone tool, but we need to figure out a way to bring economics into the picture. So there are methods. How many of you have heard of input-output life cycle assessments? Okay, so that's that 10-15% that took those two courses on campus that cover it. How many people have heard of a consequential life cycle assessment? Okay, 3 from the research lab, all sitting together there. Okay, we'll talk about this. So the idea of bringing market factors into LCA, that is a consequential life cycle assessment. We'll start getting into that idea next week. Here we're looking at a system that might be able to address that aluminum-intensive vehicle question. Okay, so here's our technology. You know, it might be lightweighting with aluminum. It might be the electric car. Right? These are technologies. These are options that producers can take off the shelf. And they're asking themselves, you know, what would consumers pay for those technologies? Would they buy them? Right? And that's where the market comes in, the reflection of us. And really, you know, what happens in a life cycle assessment is an outcome of a market decision. And that's what this framework teaches us, right? It's that those emissions are, you know, not some system in isolation of economics. They're working together. So if we're going to understand environmental sustainability, then we need to understand how those factors might play one against the other. All right, so that's where we're going. So generalizing that system, that was a system for cars, and I realized that we needed a more general system, so I quickly sort of drew this up. You know, what we're doing here within the scope of ME 589. You know, in the broadest terms, we're thinking about production, we're thinking about consumption, we're thinking about how they come together in the market, how the market leads to emissions throughout the life cycle and through the supply chains and in the end of life. And we're thinking about LCA not just as an outcome of market decisions, but as an input to policy. And this could be industrial policy, this could be technology policy at a government level, right? To inform, you know, maybe the things we could do to encourage the market to move in the direction, using the market as a tool. Right? So that's a system we're studying. In every example we talk about, we're not going to look at all these parts in every example. Toward the end of class, and maybe getting into November, we're going to look at some interesting cases, at least I hope you'll find them interesting, where we're looking at all these pieces together. But for instance, we're going to look at you know, example in water, where we're pretty much just looking at production and policy, maybe a little bit of market, not so much on the consumption side, not so much on the LCA side. There'll be a case later in the term where we're looking at an airshed example, where we're not looking as much at production, but we're thinking about consumption, we're thinking about the market, policy, and a little bit of LCA there too, right? So we'll be looking at elements of these of this system. You know, as we mentioned already, you know, the technology, you know, that's for you to learn, right? So we're not as much talking in detail, you know, how does a specific technology work, right? That's for your other classes that you might take as engineers. We're not talking about, you know, values of a society, right? Those are societal sustainability issues that you can learn about elsewhere. Of course, they're going to come up in our discussions, no doubt, but the main scope of the class is in here. Okay. In terms of direction, is it clear what we're trying to do here? A lot of you are trying to decide whether you can take the class, right? So, you know, the big picture is important. You get it? See a lot of heads nodding. Take that as a good sign. All right, so we want you to be able to evaluate sustainable design. So, you know, here's a bus that's made out of corn. Okay, not really. But, you know, it's ethanol powered at least, right? Here's some solar panels, tidal, geothermal. You know, you could have a lot of things up there. Are they sustainable design? Well, we're going to just use a simple way of thinking about this, right? So how many people know what the difference between a conceptual definition and an operational definition is? Nobody? So the idea of a conceptual definition is like something you look up in the dictionary they can't really apply in some practical sense. So let's talk about bowling balls. So we're making bowling balls. We're a company. We need to figure out whether those bowling balls are round. So we want them to be spheres, right? Perfect spheres. But and I don't know anything about bowling. Maybe we don't. But let's just pretend we do. So you look up in the dictionary sphere and you say, okay, that's the locus of points equidistant from a point called the center in 3 dimensions or something like that, right? And then you go back to your bowling ball and say, well, how do I figure that out, right? Or you could just say that's a conceptual definition, right? Not very practical. So this is like that definition. And we could look at our ethanol-powered bus, and we can ask whether that technology system is beneficial to human welfare while minimizing negative impacts on ecosystems, human health, and society today and the future, right? Well, that's tough, right? I mean, that's hard to know. That's a conceptual definition. That's like our locus of points. So this is useful as a conceptual definition for the class, but we probably need something more specific to evaluate. So the operational definition here is something we can evaluate. When we achieve a design that's economically viable, that reduces important environmental and societal concerns, that's when we've got a sustainable design. And probably to be more accurate, we would say a more sustainable design, right? Sustainability we should be thinking about as a journey, not as a destination, right? At least for the next 100 years. So this at least tells us what's more sustainable than something else. In some cases, policy may be necessary. And if that policy is realistic, then maybe we need the economics and the policy working together, right? So this is the definition that we'll use in the class. Okay, and these are, we can measure against this. We can test against this, right? It's fairly straightforward when you actually boil it down. And again, we'll be looking at this in the context of numerous examples. So there's a difference between sustainable design and environmentally sustainable design, or eco-design for short. This class is much more about environmentally sustainable design. Again, we'll touch on the social, societal issues, but that's not the main focus of this course. We're really talking about environmentally sustainable and looking at that economic and environmental component. Okay, so before we look at the syllabus, what I'd like you to do, if you got a sheet of paper, it can be an old sheet of paper, the back of a sheet of paper, it could be a gun wrapper if you write really small. But I want you to think about this question, okay? You can design a lighting system. This lighting system can be made of one of 3 choices: an incandescent bulb, a compact fluorescent light bulb, one without mercury, and very inexpensive LEDs. All right, so some of you might have been to Home Depot and you look at these LED light bulbs and they're like 20 bucks. But imagine they're a little cheaper than that. Right? This is an in-class exercise. You're going to turn this in. And we're going to do this about once a period. When you put your name on it. You can talk to each other. We're going to give you about 2 minutes, 3 minutes to think about it. And then we'll talk about it for a couple more minutes. So go ahead.
survey in front of the area.
Okay. All right, so we got burning candles, a fourth option up front here. I like that option. Yeah, my wife, she lights candles all the time, and I love it, except that she always forgets that she lit them. So, she goes to bed, and, I'm like groggy going upstairs from work, and I'm smelling candles. I'm like, well, is the house going to burn down? So that's a fourth. How many people think they got this nailed? Light bulb. This is simple, right? It's just a light bulb. You get some appreciation, right, for some of the complexities that may be involved. How many people vote for the incandescent? How many people vote for the fluorescent? LED? And how many people read the Economist article? Okay, I'm a little surprised. Okay, good. That's awesome. Okay, one volunteer, because we got to get to the syllabus here. Incandescent. Why incandescent? Go ahead.
Well, the incandescent lights, they're probably in the middle as far as cost is concerned. Probably the cheapest would be the fluorescent lights, but they have the life cycle. Their life cycle is relatively long, and the energy consumed is less. Not as less as LEDs, but I think the life cycle of an incandescent light is probably larger than an LED if you use it properly. There aren't any voltage fluctuations, so.
So a well-designed LED
Yeah.
ought to way outlast an
Really?
incandescent.
Okay.
Ought to.
Okay.
There are technology issues which you're familiar with that people are working through and are concerned about, so we're focused on them. The first incandescent light bulbs probably didn't last too long either, right? But the technology is improving, and that's why the costs are coming down. You're seeing more and more of them, right? But you hear from the gentleman in the back about some of the key issues, right? Thinking about lifetime, how long is it going to last, what's it going to cost over its lifetime, the quality of light, etc. Now, how about the fluorescent? Who wants to speak up on that one? Go ahead.
We chose it just because it's a efficient use of energy and it doesn't pollute the environment at the end of the life cycle.
Okay, if the mercury isn't there, it's not too much of an end-of-life concern. They last a long time, and today they are certainly cheaper than solid-state LED lighting. But there's some notion that ultimately, if you read the Economist article, that the LEDs are going to be a lot cheaper than either option here. How about the LED? Who wants to say something about that? Go ahead.
I think the keyword is cheap. Cheap means fewer resources consumed during production and less amount of energy consumed in their operation. Of course, as the article discusses, that may lead to overuse, but I think that shouldn't be the reason why you shouldn't go ahead and design cheaper, less energy consuming alternatives like solid state light.
So people need light, so you might as well use the cheapest and most energy efficient alternative, right? But as the gentleman points out, there may be a demand for lighting that is not fully realized because of the costs today. So, why bother with the candles? Just leave all the lights on because it's cheap, right? And that was the concern raised in the Economist article. All right, it's just actually a very interesting way to think about it. So we're going to talk about traps, trade-offs, and triumphs as the semester goes on. The question is whether the LEDs are going to be a triumph or not. And that's a characteristic of a triumph, right? It leads to overuse. All right. So these are the issues we need to think about, right? Maybe doing a good thing, we're actually going to increase the overall impact on the planet, right? It doesn't mean don't do it. It means, find ways to manage the situation, right? Maybe that is really not about the light itself, because people want light, and light's a good thing for safety and other reasons, but because maybe we should be thinking about the power sources for those LEDs, right? And the power plants, right? We don't have to use coal. Right. So we'll be asking questions like this, not just to keep you awake, but to feed some discussion. And today we're cutting it off a little bit short because we need to talk just a little bit about our syllabus. Okay. I'd like to begin by introducing Sarang Supekar. Sorry, I got your name wrong. He's over here, hiding behind a pole. I don't know why that is, but he is a graduate of the course. He is an experienced GSI in this course from the winter of 2011. And he's also a pretty darn good PhD researcher. I've had the pleasure of working with him for several years now. So he will be we're calling him the GSI 1. Okay, so he's basically your point of contact. Now, we've got 50 off-campus students, as I mentioned before class started, and there's going to be a lot of grading involved, so we've got GSI help on grading. Pratish Roy is going to be helping out with the grading. You won't see too much of Pratish. Sarang just is going to be the point of contact, because I'll keep it easy for you. And he's going to be involved with all facets of the course, and certainly aware of the grading and contributing to that, as well as helping out a large part of the logistics, and even helping to create some of the homework assignments. Okay, so these are the people involved with the course. Office hours. Sarang is having his office hours Monday and Wednesday from 10:30 to 12:30, and that'll be in 2190 Gigi Brown. WebEx is an online communications tool. It works great for office hours, and it also allows our friends off campus to participate in office hours. So I have WebEx office hours on Thursday evenings. Tend to be very heavily subscribed at that time. It's also after my kid goes to bed. I might actually have to move this to 8:30, but I'll let you know if that happens. Sarang is having Tuesday and Thursday evening. Well, let's see. We may have to modify our times, right? So we're overlapping for an hour. I just realized. We could compete a little bit on office hours and see who they come to. My bet it's you. But we'll basically let you know that we've got WebEx office hours, we've got in-person office hours, and my office hours will also be after class on Tuesday for folks on campus. Okay. If you send us an email, we'll try to get back to you as quickly as we can, but put ME589 in the subject line, or you're pretty much doomed on a response, because we get a lot of email. As most of you know, I serve as graduate chair in mechanical engineering, so I get a lot of email. 589 is a priority, but I need to know that, especially before I learn all your names. It's coming from the class. There's a course pack that you're going to need, particularly for assignment 1. The bargain price is $25. We've taken some key sections from books and have compiled them into a reading, which makes up for the courses that most of you didn't take, at least with respect to understanding the basic environmental science as it applies to this class. Okay, so you can get this at Dollar Bill Copying. It's about $25, as I mentioned. You can go to www.dollarbillcopying.com. Okay, and that's in the syllabus too. Or if you look at the electronic copy of the syllabus, you can just click on it, and you can get it online also. Okay, that's a course pack. In terms of grades, we do something a little strange in the class. We have an optional final. So you're going to have 2 exams, each worth 20%. And the lower of the 2, if you choose to take the final, you don't have to take the final. But if you do, it replaces the lower of your in-class exams. Okay. This is actually a fairly easy class, but what's hard about it is keeping up and sort of there's so much material that, especially on the first exam, people tend to have, they either think it's easy and start studying late, or aren't quite calibrated to the questions, and usually it takes a little bit of adjustment. So we want everybody to get an A. Hasn't happened yet, but we're happy to do it. If everybody earns it. So we want to give you that opportunity. You've got a course project. I'll say more about that in a second. That's 30%. Your homework assignments, there's 4 of them, going to be 20%. And participation is 10%. Now that participation for folks on campus is going to be comprised of your responses to in-class questions. Okay? So what you're going to do is take your in-class responses, and you're just going to pass them all the way down to the right. In fact, why don't you do that now? Put your name on it, and it's my right, your left, my bad. And Sarang is going to pick them up. And we're actually going to look at what you said. And usually the way we do this is, if the answer was brain dead, you get like 60%. And then if it was conscious, it's 100%. Right? I mean, we're not judging right and wrong, but we want to know that you're thinking. And that's all we're looking for. Now, if you're thinking, even if we don't agree, you get 100%. All right? So responses to in-class questions, 5%. Your attendance is 2.5%. Right? That's a tragedy of the commons thing. If the folks on campus just watch the video and don't come and contribute, that really ruins the experience for everybody. Right? So just putting your name on that is going to get you 2.5%. And then we're going to have our own evaluation based on our interactions with you for the other 2.5%. So that's going to add up to 10%. For the folks off campus, we're going to have some forums where they can contribute. So for folks off campus, we're going to put 4 questions on the forums. And folks on campus can contribute to that too. But basically, we're going to try to put some controversial question related to the course, related to sustainable design. And then we're going to let the students go and let people take sides or offer their input on those questions. And there are going to be 2 questions in the first half of the term and 2 questions in the second half of the term. And we're requiring the folks off campus to respond to 1 in the first half and 1 in the second half. So either question 1 or forum topic 1 or forum topic 2 and forum topic 3 or forum topic 4. And it's spelled out in the syllabus here. And the responses on the forum are going to be 7.5% of participation. And then the other 2.5% is going to be our own subjective evaluation. Starting Thursday, please bring a name tent. Okay? Now, it's going to take at least a month for me to call on everybody once. So you're going to think, 2 weeks from now, like, why am I putting this name tent up? We could sort of evaluate that. We don't want to. Try to, we'd like to learn names, as quickly as we can. We'd also like to call you by your name, too. Okay, so bring a name tent. There's a template on CTOOL in the resources folder. Okay. Questions on participation? Is it clear? Okay, this is a schedule. In part 1 of the class, we're going to be talking about methods, LCA, consequential LCA, input-output LCA. We're going to review topics you've seen in Econ 101, maybe in high school even, net present value, supply-demand curves. And then on the 22nd of September, that's when Assignment 1's due, before class. We're going to have a roundtable discussion on Assignment 1. So I'm just going to throw some questions out there. You're going to answer them and hopefully talk to each other. Okay, and I'll sort of moderate that discussion on the topics or review of environmental science. Okay? Part 2 is on sustainable design of watershed quality. We'll do some basic environmental systems analysis. You'll learn what biochemical oxygen demand is. We're going to look at a case study of unused medications and take-back programs versus flushing them down the toilet or putting them in the trash. We'll look at these 2 case studies, the Big River and the unused medications. We'll look at them quantitatively. You'll get exposed to some applied optimization in the Big River problem here. We'll look at in Lecture 8. Then we're going to talk about products. We'll talk about sustainable design processes. We'll talk about sustainable design examples. How many people have used CIMAPRO before? Okay, nice. About a third, or a little less than a third. All right, so we'll introduce you to CIMAPRO. We'll go through an example. You have a homework assignment, original homework assignment that is going to ask you to use CIMAPRO. Then we're going to look at examples in the life cycle. So we're going to look at materials just ahead of exam 1. We're going to have a review, a roundtable for all our exams. Okay. So materials, and we're going to look at manufacturing, and we're going to talk about end of life. That's going to take us through product. Then we're going to talk about air. So we're going to talk about point source models for air transport and pollution. We'll extend that to line sources like roads, area sources like cities. And then we'll talk about power plants and how their emissions as networks of power plants respond to loads at a macro level. So think of the grid and how the grid might respond to electric cars and what are the associated emissions. So we'll talk about economic dispatch from power plants here. That's a nice segue to transportation, energy, and policy. We'll look at some of the climate change targets that the IPCC, the Intergovernmental Panel on Climate Change, has set, and what that might mean for cars. We will look at some case studies of the corporate average fuel economy standards. And when we talk about that whole consequential LCA system, we're going to really nail that down with this case study. And then we're going to end that section with another roundtable because we got a lot of mechanical engineers here, and folks like talking about cars. So we'll talk about transportation, we'll talk about energy, and we'll let that discussion go where it leads us. Okay. In December, we're going to have 2 periods of debates if everything goes well. You can look at the winter 2011 video, which is on CTools, session 2, and you can peruse some of the debates, maybe session 2 and 3 actually, the debates that we did a year ago in this class. They were amazing. You have an option to be involved with a debate for your term project. So, just as an example, is local food versus sort of global industrialized food sustainable or not? So you get 2 or 3 people on each side, and we use the Oxford style of debating. For anybody who's seen or listened to Intelligence Squared podcast on NPR, you might be familiar with that format. And basically duke it out intellectually there. Okay, so we'll talk about the logistics of that if you're interested on Thursday. For those of you who do not do debates on campus, the debates are only available to folks on campus for the obvious reason we have everybody up here in front of the room. The last day of class, for those of you who do not do debates, we'll just take a few minutes, probably 2 minutes or 3 minutes, just sharing with other folks what you've done for your term projects. And we'll talk more about the term projects on Thursday, about what they are. You can go on to CTools and look at a large number of archived term projects and get a sense of what the term projects are. They are in the scope of the class, meaning they deal with money and the environment, and usually they involve a research topic, something you might be doing for your PhD or master's research, or some type of educational case study or something of a personal interest. Okay, they usually fall into one of those 3 areas. And we only got about 2 minutes left. Sarang, am I missing anything critical? You don't think so? Okay. Then let me just release assignment 1. There are a few things, because we went really fast. I normally like the class to be more interactive, but the first day is really packed. And we need to understand why we're here, where we're going, and what the topics are going to be. So you can decide whether you're going to stay or not. We hope you all will. We got a few extra seats. If you want to call your friends up, that'd be fine too. But this is a class where you get your first assignment on the first day. Basically because you need the time and you're probably not as busy this week. You're going to get your course pack. You're going to click that CTools link that Sarang sent out. You're going to see basically 5 reading assignments. I think it's about 100 pages. About 100 pages. It's not unreasonable for 2 weeks to do. It's a little bit more than 2 weeks. Yeah, a little bit more than that. And you have a lot of questions to answer. You can work on it together, that's great, but you have to answer the questions yourself. Okay, so the honor code is something we take very seriously in the class. So we can tell really fast if folks are copying off each other, and we're not very kind about it. So work together, but put your own solutions down and get started on it early. So it's about 100 pages, and as you're reading, just have the questions there, and form study groups and get it done. It's actually we got really good feedback on assignment 1 last year, so hopefully it'll be the same this year. Okay. So on Thursday, we're going to start talking about LCA. I'll give you more detail on the term projects. I'm going to be much more specific on the course objectives. They're laid out. They're also on C-Tools, and connecting them to the lectures. So a little bit refresher from today, and then we'll dive into it. So thanks for coming, and we'll see you Thursday.